Nice, I got some plots.
Yeah, we got some plots. All right, you doing the post, Anshul?
Yep, it's already out on the Dyad channel.
Mm-hmm. All right, and the YouTube one is also up. Cool.
Yep.
All right, so greetings, everyone. Today is going to be our first Dyad Day. I mean, so we're still kind of settling in on names and what we're gonna call all these things and everything. But oh, and right now it's all showing Anshul. I don't know why it's preferring your beautiful face there.
Uh, at least on Twitch, I can see you, and only you. I don't see me.
Okay. My Riverside is only showing you. All right.
Huh.
Well, okay. That's fine. Let me do the picture-in-picture slide. Just
At least on Twitch, I can see you, and only you. I don't see me.
All right. Just and so this is a I'll say it's an exclusive drop to everyone. It's like a Beyonce album. There's no information given beforehand. We're just going live today, kind of as a test stream. So if anyone are these hardcore Julia people inside one of these channels that really follows a lot of what's going on, you will have you will have the inside information to get this. Other than that, nobody else knows, so you can feel very hip about this if you're in the know, because this is just our test stream, right? So I think it might be good for everyone here just to give a quick introduction, just so that way everyone knows who everyone is. So I'm Chris Rakakis, if y'all hadn't heard of me. I do the differential equation solvers and a lot of the modeling toolkit in Julia. Now I'm the chief architect of Dyad, and that's what we're going to be showing today, this fancy little agent that's able to do a lot of modeling and simulation. And so I guess the other folks here, maybe we could just go John, Anshul, and then Anas.
Hi, yeah, my name is John Batey. I work at Julia Hub, and I've been here since February working on Dyad, and excited to be part of the stream.
Yeah, I'm Anshul. If you're in Julia, you might have heard of the plotting library Maki.jl. I work on that, but I also work at Julia Hub on the Dyad simulation product. And I also do geospatial stuff, so lots of things.
Yeah, I guess my name is Enes. I'm the team lead for AI at Dyad, and also the lead developer for the agent. And nothing more special other than that, really. Just look forward to this.
Oh, don't worry, you're special. Alrighty, so what we're going to be doing today is we're just going to go through building models with the agent. So what we're showing here is this new agentic system with Dyad, and if you're like, oh, I didn't know that Dyad has this agentic system and everything for people to use. Well, the thing is, it's not for people to use yet. So it's really just kind of for us for now, right? So but it should be coming out fairly soon. It should be coming out very soon. We're looking at a very early December launch date. We've already run workshops at NTNU. We've run workshops at MIT. We've got students installed. In fact, one student basically did their entire thesis in about 2 weeks. They were spending like a month and a half or a year and a half building out models for their thesis, and then decided to start using the agent instead. And boom, in 2 weeks they had a whole thesis together. So yeah. So we've been getting this into the hands of people, but we thought a great way to kind of start just working with Dyad and really kind of starting to use this is to just show people live and take ideas. So if people do have models that they want to work with, they would be like, oh, I want to build a model of XYZ, right? Throw this into the chat. We'd be happy to take live suggestions. And we'll have to see how this goes. But again, this is our trial run. Otherwise, we'll kind of just start going off in a kind of pre-canned area. So, but I think that we might want to just start with something. Maybe John might have a model in mind or something that just like, okay, what's one that you can just start with and just start building out.
Yeah, I always want to go into the thermal space. So,
all right.
How about something like a room that gains heat from the outside, has a heater, and loses heat through the walls.
Okay, so let's make a model of a room which is gaining gaining heat through the walls.
Losing heat through the walls,
Yeah,
gaining heat.
Okay.
Yeah, gaining heat from the sun and the
Okay,
heat.
so a model of winter.
Yep.
Losing heat through the walls and gaining heat from a
Solar.
few sources,
Yeah.
such as solar,
And a heater.
a heater, and an Intel-based computer. AMD wouldn't heat up the room enough, so
Did we add
have
thermal
this.
components, by the way?
And a few humans.
A few humans, including one playing on a
Right.
drum kit.
Yeah,
Right?
but
I don't know if you see, I got this drum kit back here. Right? So I'm sweating every time I'm using that, even in the middle of
Chris, do you want to ask it to like what the plan should be before we set it out?
That's a good idea.
Plan out the model before continuing. Is this a good way to do it?
Yeah. And did we add thermal components, by the way, or no?
I believe I did. I think I just added all the translational thermal. Yep, thermal components are in here.
Beautiful.
Alrighty. Are we all good on this query? Yeah, it's like Twitch plays Pokemon except with modeling.
Yeah, just plan out the model and that's it. That's
all
what
right.
it does.
All right, we got a comment on Twitch of someone saying add a heat pump.
Add a heat pump. Oh, we'll get there. We'll get there. By the end of this, we'll have a complete, recreation of one of Carrier's HVAC systems or something. Yeah, so we'll see what we get to. Now,
Intel-based computer.
Yeah, it's gonna figure out the wattage of this computer is probably like 1,000. You can hear the fan going, right? So it's a whole thing. Yeah, so I see the add a heat pump on Twitch, but I don't see it in the public live chat. I think I might have accidentally set the Riverside chat to just the YouTube one. But okay. Yeah, but we'll add a heat pump. Don't worry. We are pro heat pump here. We are environmentally friendly, and if you are actually in the Massachusetts area and you have a heat pump, you can get a rebate on your electricity. I just signed up for that, so my electricity cost is about 50%. So maybe we can actually look into the whole energy generation there and see if we're actually if the grid is powered by if the grid is powered by fossil fuels, how much we're actually saving with that heat pump. But okay, compilation failed. So one of the interesting things about Dyad's agent, right, is that so Dyad as a language, let me just start to show this so that way people can kind of see here. Right, Dyad as a language is a very high level language. It's an acausal language. Ansho, what's up?
No, I just realized that I know the reason why it's doing this now, because we haven't updated the agent yet to the new Dyad syntax where quotes are docstrings, but yeah.
Okay. Yeah. So again, this is a pre-release version. We're just going for it, right? This is why this is an exclusive stream here. We are not ready for the general audience. This is not the final release, but we're getting such good results that we just wanted to start showing people. So yeah, there will be a few things in here that we're just going with. But yeah, so you can see here, it's a high level language. If you know like Modelica or Modeling Toolkit, it is one of these acausal modeling languages. And because of that, it has things like units, it has things like connectors, and we'll show this as it goes along. But effectively, because there are units and things tied to these equations, it can do a lot of static checking and give you a lot of compile time errors. And this is what you see. So it's finding out that this is actually an invalid model that it was writing. Well, I guess the invalidness might have been due to some comment syntax, right? But yeah, it's going to be able to look at a lot of different things about what are the equations and what's the structure of the equations and things, and try to be able to get a correct model before it even tries to simulate anything. And this will give it a much higher chance of giving a more accurate model. So we'll see this agent kind of running through all these different steps. And of course, this is still the early version. It still has a bit of latency because it's not using the newer version of Modeling Toolkit that cuts that out. So there's a bit of jank of what we're showing here, but we got the pizzazz of a live show anyways going.
Yeah, so usually Just a quick comment here. So after compilation, it'll inspect the model, and all the, usually you'd have to write out the MTK code, but inspection here means that it'll look at the equations, look at the unknowns, it'll make sure that it's balanced, it'll check if it's a DAE, and then that's the first part of the inspection protocol that it follows. And then after that, it'll start to simulate. It'll do these checks that we'll see later on, where it'll simulate the original model given its physics, and then match it with what the expected value should be, and then it does this backwards. So here's an example of this, and
that's a lot.
The temperature range?
That's a lot.
Yeah, I mean, maybe it was so used to cooking turkeys that.
Well, we did say Intel processor, so
we did say
Intel's processor.
And that's what happens when you just add heat, right? So.
Yeah. The room is heating up to unrealistic temperatures. All right, so this is a validation failure. I don't know. I thought that was realistic. I mean, but I grew up in California.
So this is the cool part. So can we zoom through the? By the way, for some reason the I don't know why it's smaller on my screen. Like, it's not a full screen. It feels like I thought you had an ultra wide monitor. I don't know why it's coming up for me.
I do have an ultra wide, but it's kind of cut because of the people who are having other things on the side and some of the Riverside overlays and whatnot.
Oh, I see.
We'll definitely get this going
Cool.
better in the near future.
Right. So this is the cool part, right? So it simulated the model, and it realized that it got unrealistic values. And typically what you would do is you would go ahead and say, okay, it's unrealistic based on what? Well, if we take the model that we have and we put it towards steady state, then these are the typical values that we expect, and that's what it does for the first step. So you can, and then it goes through this forensic protocol which is it's walking through the equations for each step, and it's finding out where in that chain is there something that's unrealistic or doesn't make sense, and then it'll zoom into that going onwards. So here it is.
So the physicist is correct. The steady state temperature is indeed 59 degrees Celsius. I mean, those Intel CPUs, So you heard it here first, kids. Don't run your computer, too long. If you're playing StarCraft, only play one game at a time, or get an AMD.
I think that's actually, that's a really cool interaction, right? Seeing that that the agent basically just looks at all the heat that's coming in, and it knows the heat loss, heat transfer coefficient through the wall, so you can effectively find what the steady state temperature would be from that. And now I can go and decide, should I reduce the heat? Do I need to lose more through the walls? Whatever, right? So.
Yeah, I think it's like, I think it actually thought that the Intel CPU was
it's trying to get you to turn off your computer so you don't melt.
It might be. I mean, maybe we just tell it to add a controller instead of changing the temperature values.
Yeah, that would be cool.
Right, like you could tell it to add and tune a PID controller or something.
Well, I think it's got to get into a realistic range here first, and then we'll add in a heat pump, and then we can put the controller on the heat pump.
Yeah, but it's cool that it doesn't just hand something over to you. I mean, the key is that it has to walk through the physics and be like, this has to physically make sense. And there's all this orchestration on the inside that forces these kinds of analyses to occur before something is handed off, so that things get double checked and aligned with physical expectations. And up front, we didn't exactly say what the temperature should be and or anything of that nature. We just kind of gave it a very broad starting point. And this is usually what happens. If the original query that you provide is not very specific in the actual model details, then the agent is going to fill in the details on your behalf. And then if it fills in those details and the outcome of that is something that seems unrealistic, then it's going to kind of claw back and try and adjust what it filled in on your behalf until it makes physically sense. And you could always hit escape on this point and then you go ahead and be like, I should have told you this piece of detail instead, and continue on. But what we're doing right now is completely fine, and it's actually figuring it all out.
Yeah, what did it set for the ambient temperature? We probably should have told it that.
Ambient is 20 degrees Celsius right here.
Okay.
Yeah. In fact, actually, Anas, with the current version of the model, is it? Oh, I love this. Okay, in the chat, or actually, in the chat it says heat output too large. Switch from i9 to i7. Yeah. So no. So in the current version of the agent, if I open up this file, it's fine. I just can't edit it, right?
Yeah. It's completely fine to view and do all that stuff. Yeah, unless you just like hit
Alright.
actual save, you can definitely view.
Yeah, don't render diagram either.
Yeah.
Yeah, I'm not going to render the diagram yet, but okay. So we have room air, which is modeled as a heat capacitor, and then we have ambient temperature, which is a fixed temperature at 293.15, which is 20 degrees Celsius. We have the walls or thermal conductor. I don't know if that conductance value is good or whatnot. I guess we can dig into it and start to ask it what kind of wall did it think it was trying to model? You know, like
Yeah.
Mhm.
Yeah. That's perfect. Exactly. Yeah, because it filled in on our behalf. So.
Yep. Electric space heater. It actually did put the Intel computer as almost effectively a second space heater. And this drummer is going.
Elevated metabolic rate due to physical activity.
350 watts. Like, this is a Neil Peart going right here.
I love that. Oh my god, that's so funny.
Yeah, so it's created quite the model all automatically.
Excellent, and it's given us some plots too.
Success. All right, and it's gotten to the bottom. Let's see what it says it has created. I mean, we could start to go over it already, but it has solar radiation, it has electric heater, it has an Intel computer, it has 2 resting humans, a drummer, and total heat output of over 1,000 watts. Now we have all these elements which we saw in the simulation results. Let's actually check out these simulation results. These should be inside of our assets folder, right? So room heat balance over time. So you can see that it starts from an initial condition and then flows into a transient. Now I guess, so it's modeled the solar input over time. I think that the frequency is a bit off here though, right? I mean, it shouldn't be a 12-hour cycle. It should be a 24-hour cycle, right?
Yeah, I think night and day. Was that its
Yeah, but I mean, you know, it should cycle once in a day, right? So I don't know why it cycled twice in a day. So we could correct that.
Yeah.
And then we should probably make that initial condition probably at the ambient temperature, right? That because it's kind of an oddity out here. So let's do these two things.
But
So,
it is kind of nice to see it warm up from. I mean, it gives you a chance to see the heat capacity part, right? That came from the air.
Oh yeah. So okay. So maybe like I just got back from Thanksgiving where I left my heater off the whole the whole holiday. So let's start this off from ambient temperature. Let's lower the ambient temperature to something that matches, December in Boston.
And Chris, ask it to discuss with you before it implements, so that we can at least see what it's going to do before it does it.
Okay, discuss with me before implementing.
Yeah.
All right. So there's those two things, and then the day cycle should be 24 hours. Yeah, let's start with these modifications.
All right, and then after this, it's the heat pump.
After this, yeah, we'll get into pumping the heat. I mean, I think that the main thing is that we needed to change the ambient temperature down to something that requires a heat pump to then stabilize it, right? So
that makes sense.
I mean, to be fair, this is also not very winter-like temperatures. We should probably tell it that the outside is like 0 degrees Celsius or so.
Well, that's what I was just saying, right? Just so current the room starts at 22 degrees. I'm saying start at a cold start scenario. Ambient temperature.
You left for
daily
Thanksgiving
high.
with the heater off.
We can either. So. Yeah, let's use option B. I think having having a time varying temperature that matches the averages throughout Boston's winter is probably good as a cool thing to show. Current 12-hour cycle, proposed 24-hour cycle. Yeah, that's you know, I don't know why I did a 12-hour cycle. So solar timing. Should solar start at minimum? Start the simulation at noon. Actually no, at midnight. I just got home and am really wondering when it will be warm enough to fall asleep. Right. I don't know if you guys ever did this, like where you're like, okay, I'm going to Thanksgiving, and I just completely turned off my AC. I come back to my apartment in Boston. And I was like, oh god, it's like 40 degrees in here. I'd never. I learned to just set it low. Okay. Let's see. Yeah. So let's run the simulation for 48 hours. Heat should turn on when I return. There we go. Let's see how this goes. Now I don't know if it's going to think that the only heating is my Intel computer in the solar heater, but we'll find out. One guest is waiting. All right, so we're also introducing someone. So while this part of the model is running, we're going to get a new person coming into here. Sebastian, are you able to hear us?
Yep. Hello.
All right, give a quick introduction to yourself. Who are you?
Hi, I'm Sebastian. I'm a software engineer at the Julia Hub, and I'm working on the model discovery and model optimizer capabilities.
Mm-hmm. Alrighty. So I'm getting an echo of myself through you, so please put on headphones. Alrighty, so we got this model going. Let's actually check also at the same time. Let's check how the dyad code is evolving. So okay, this should be the version that it's in looking at. So let's take a look at this here. So change the frequency so that way this frequency better matches a day and it peaks at noon. And the ambient signal is now going to be so the ambient signal is now going to be a sine signal, just matching Boston December averages. I don't know how to do this in my head for what the heat capacity should be, but I don't know. John, does that look like in the right range?
Let me look. What is that? What is it? Is that 50 cubic meters of air? Is that right? Is that what it says?
Yeah, that's what it's saying.
Okay. Let's do some work on the side.
Engineer on deck.
All right. Yeah, we got our human agent double checking the agent that's in control.
Is it done simulating in the meantime? I think it was at the. Ooh, okay.
So it's running. And the initial condition, it starts at ambient at midnight. Yep. So I think at a high level, the model looks correct. And I think this is the one thing I really like with the dyad version of the agents, right? I mean, it's spitting out, this is the entirety of the code it's writing, right? And you can very easily kind of just eyeball the model, right? Because again, it's this difference of the model, the agent's not actually doing implementation, right? It's doing high level specification of model, and then all the symbolic simplification and everything really takes care of all the other details below, and it's able to use a lot of these pre-built components from the standard library to ensure that a lot of things are correct by construction, right? So that's why some of the stuff that we're doing here, we're playing around, but it's really seriously creating models that are able to start giving you accurate results because of this way where the agent doesn't necessarily need to know everything in order to get there, right? It's able to use a lot of pre-built tooling. Okay, it's saying then that, oh no, the room never reaches 18 degrees Celsius. It only gets to a maximum of 10 degrees and settles at 4. This is a failure. You'd be freezing. All right. So, well, this seems like a very accurate model of Boston. Maybe yeah, the heater power is too low. So I think that this means, yeah, we do need our heat pump. Let's add a new heater to the model. This is a heat pump. Make it be a simple model of what should I say, like a high performance heat pump, or
I think. What did the gentleman in the Twitch chat? I think, did he have the suggestion?
the person. I don't want to prescribe
Sorry, whoops.
gender.
Yeah, whoops. Yeah.
They just said add a heat pump.
Whoops.
So I don't know. I mean, yeah. Let's just say, make
Add heat
it
pump.
match the average output that a heat pump generally has. Oh, and it looks like the person in chat here, it has some extra information. They said 5 kilowatts is normal for homes here. So actually, let's see what it gets to. Let's see if it comes up with 5 kilowatts.
Are you running the agent locally? Yes. This is on a local Windows machine. It's Windows, right, Chris?
Yep. This
No,
is
no,
a
I think
Windows machine.
I think the question was, are you running the LLM locally? And the answer is no.
No.
No, it's based off an Anthropic agent, but it is using our own agentic system on top of that. So
Based on an Anthropic model, yeah, and
yeah.
we built an agent on top of it. So what did it say? Did it say 50? Oh, it said what is it?
1200 BTU or 4000 watt heat pump. All right.
Yeah, that's about 4 kilowatts versus the 5 I was suggesting.
Oh,
Oh,
not
that's using
bad.
it's using a mini split. All right. Yeah, I guess let's check in with our human agent here, John. The capacitance, the heat capacitance. Did this calculation seem to work out in a realistic manner? Is this something that we could trust here?
Yeah, that's a reasonable number. I mean, the 50 meter cubed, right? You can just assume something was like 5 meters by 4 meters by 3 meters, right?
Mhm.
Something.
Mhm.
So that's a reasonable value, and then that's the CP of air and the density of air. So, I mean, we don't have our room is just air, right? So a real room would have furniture and all kinds of other stuff that would add capacitance. So we're just heating the air, so it seems it's fine.
Mm-hmm. Yeah. Okay. Well, this is a bachelor pad. There's no furniture. There's just
There's nothing. Yeah. Just
There's
air and humans playing drums.
Yeah. There's a mattress on the floor. That's about it. And an Intel computer. And an Intel computer.
And an Intel computer and a human playing a drum.
Yeah. I mean, it's not unrealistic. It's not unrealistic. So okay, so it looks like it's now correcting this, and it's now going to do this new run based off of having this heat pump.
So how did it treat the heat pump? Just a prescribed heater, or is it doing anything else like tracking the energy consumption?
Yeah, let's look at heat pump. It's just doing this as a fixed heat flow.
Just a fixed heat flow. Okay. Yeah.
Yeah.
Okay, it does have a COP number, right? Output is a conservative estimate at cold temperature COP. Okay.
Someone's toast just finished.
Yeah, the toast is finished. It's not mine.
Excellent.
I mean, we don't have a toaster in this model, but I guess an Intel computer can be also treated as a toaster. Oh, it did lower this down to 150. Let's see. Okay. Oh, and that's just hours or seconds and hours. Okay. Yeah. I mean, this looks all like it's going to be right to me at this point. I guess we'll see in a second here. And boom. Okay. Excellent. The heat pump works perfectly. All right. You can sleep comfortably in just 8 minutes. Wow. That's I don't think that. Let's look into this. Let's look into this. Um. What are the names of the new plots?
You can also scroll through the Julia REPL output, right? And it'll show you the plots that it saved at the end. Oh, so it just did a computation. It didn't actually do the plots for you.
Oh, okay.
I can
Yes,
create those.
please generate.
Animations are nice too.
Yeah, we'll get a whole Geomachie animation going with the room heating up or whatnot. Oh, we did not post this to. I was also going to post this to the Discord. You didn't put it there. Oh wow, okay, it did this in a GKS window.
Yeah, it's gonna save the plots, right? It is saving them.
Yeah, it's saving them as well.
Mm-hmm.
Oh, you should have told if this house is in Budapest. And then had in the background, my house in Budapest, my hidden treasure chest, my golden grand piano,
Oh, nice.
my beautiful Castillo you. Alright, so it goes from this ambient temperature, you come in, and then it's saying that, yeah, it's able to get to sleeping comfort pretty fast here. Is that can't be right? 10 minutes for the heat pump? Oops. How do I get it to zoom back out? Nope, that's not right.
I think you just
Control click. Does that work?
Oh, that works too.
was that a VS Code thing? Like you zoomed in and
Yeah, it's a VS Code thing. Okay, so let's see. Does it really take just 10 minutes to heat up a room with one of those heat pumps? I must have a heat pump that's not well sized for my house then. I just realized I probably need to get a new heat pump.
I mean, you have a heat pump sized for a house, not for a room, right? So.
Okay. Oh, that must be it. Okay, so it's a heat pump size for a house that's now only heating up a room.
That number is a house number, right? Like the 4 kilowatts. That's not a room.
Okay. Oh, so should we change the square footage of the place to be more for a house?
Or reduce the output from the heat pump either
Okay.
way.
what would be interesting is if you just mention that point instead and see what the agent says as well. Like that it actually recognizes that, oh, this is for a room versus a house. Like
Yeah, you can just say I'm simulating just a room, not a whole house, and you can ask it what it would do.
All right, let's see what it does. And I would expect the thermal capacity of the interior in the range of 5 to 10 kilowatt hours per C. I don't know how to translate that to our units here immediately. Maybe John, maybe you can take that. Did you see the?
Is that in the,
message in the chat here.
is that in our chat here or in a different chat?
It's in the Twitch chat. I would expect the thermal capacity of the interior in range 5 to 10 kilowatt hours per C.
Let's see.
I think the audio, sorry, the video is dropping on. Oh, there it is. Never mind. That's just me.
Mm-hmm. Yeah, our Riverside backend is not going to be the complete thing. Oh, so okay, so the chat that is showing inside of our backend is just going to be the YouTube one. I see that's going on. So yeah, is a heat pump modeled as a simple 4 kilowatt hour source? Or what is the component that the agent is using? I think I missed that part. Yeah, so let's actually go back to the model here and let's inspect where we're at, right? So okay, so we have our room thermal model, which has room air, which has, it's just modeled as a heat capacitor. The calculations right here, and this is the capacitance that we get, which John double checked and said that's about in the right range. And I think that in the Twitch chat, there's some discussion about whether this is going to be in the right range. So, I guess John can give more comments on that. But then we also have the ambient signal, which is just the ambient temperature. This is a prescribed temperature by a sine wave that is just matching some Boston averages. We have the wall thermal conductance, right? So just the conductance from the room to the ambient, right? This is just says it's using a typical room with windows. Might be worth double checking this value right here. All right, this is a 200 watts per K. I guess I don't know why these are flipped units, but we can maybe chat about that. Then we have a solar signal, so solar radiation through the windows. Has a day-night cycle itself, and so it talks about the solar radiation here. We have electric space heater sitting on my desk, just 200 watts in the low setting. We have a heat pump, which is set at a 4,000 watts or 12,000 BTU setting. We have an Intel CPU, which is running at 150 watts. 1,500 would have been what it started at, but no, it's 150 watts. We have 2 resting humans, each at 100 watts. And then behind me, we have a drummer going at 350 watts. And I kind of refuse to believe that a human drumming is actually more than Intel computer, but maybe we could double check that later. And we have a temperature sensor, so just to monitor. So this is just the model that we have. We then connect this all, and boom, this. So that's our current model, right? For everyone who just kind of joined in here. So what we were looking at last, right, is we're looking at here. It says that basically heats up the room in about 8 minutes, and I believe that it's because the heat pump here is kind of well, it says that this is typical residential heat pump for a room this size, right? I guess so.
Well,
so yes.
It did make an update at the end. It actually said it was an overestimation. If you just scroll all the way to the bottom, the final thing that it said.
Okay, so this is size for small apartment, 1 to 2 rooms, typical for 450. 400, yeah. So, but we're at 540 square feet, which is a small apartment. Verdict. It thinks that we should be using a 4,000 watt. So yeah, should we change this, or should we now start looking into some control strategies on trying to then and trying to try to save energy with our sleep? I think if it's telling us it's in a reasonable range, that's probably okay. But let's now try to do something here, right? So what kind of so the heat balance over time. So the heat sources over time. So the heat pump is just going to set as a fixed source, right? And maybe then we want what we want to do is we want to make it so that way it's not just a fixed source, and we actually just have this turning on or whatnot, right?
Yeah.
To call in John here a little bit, you know,
I mean,
when we do like
you
a
also
bank
you also
controller.
have you also have
Mhm.
25% other heat. I mean, the other heat that we added is about 25% of what the heat pump's providing too. So
Yeah. Which seems a little crazy, but I mean,
you
we,
can
we could double check those values.
well, let's assume that those parts are fine. Let's see if it'll add a control. See if it'll control the heat pump heat
Yeah.
to match a desired room temperature.
Now add a controller to control the heating from the heat pump to make it stay around a desired temperature, just a good, slightly cool temperature for sleeping during the night, but then something more comfortable for being outside of blankets during the day. I don't know if you guys all do this as well, but like I have my Nest set up so that way it's slightly colder at night, so that way I just have a ton of blankets on, and when I wake up, I'm always like it's super freaking cold. So I'm trying to see if we can get it to do something like this, and so like have it so that way like the Nest is set to like 68 degrees at night, and then we wake up it's already set to 71 degrees. I mean, it doesn't work out so well for me because I only sleep about 2 hours, but it's a thing. So let's see. Okay, let me design a temperature controller for this. So the set points. I don't know how to read. I don't know how to eyeball Celsius. But I assume that those are good at sleeping and awake temperatures, right?
No, that's cold. That's very cold.
20 to 29 degrees is not cold at all.
20, it's like pretty high AC temperature. I usually do like 24.
Yeah, well, let me double check on my computer
That
over
is
here. What
not
21
cold.
degrees is fair? So
Dude, you're
CS
Canadian. You
Fahrenheit.
don't count.
Dude, 22. That's shorts and t-shirts.
Oh,
Yeah,
21 is great. 21 is great.
Yeah,
21 is great.
22 is almost 72 degrees Fahrenheit. That's
Yeah, all right, all right.
that's pretty warm.
Come on now.
You set it to what? 74?
Dude, I grew up at like 19 degrees north, all right?
Okay, all right. You need some thicker blood, I guess, huh?
Oh, Chris, we have an interesting comment in the Twitch. The person said you could minimize electrical power P, which is a function of P equals Q over the coefficient of performance. I'd be curious to see if we can figure out the right variables for COP.
Okay, yeah. Well, let's do this in a second. Let's do this in a second here. Let's start to get through. Okay, so the control strategy options, time-based switching, on-off thermostat, so a bang control, or a proportional control, so a variable speed heat pump. I actually just got a variable speed heat pump, so I would like to see, maybe the thing to look at would be what happens if with a proportional control versus a bang control. Just to kind of see what the difference is between like these new variable speed heat pumps and the energy efficiency you can get versus the bang control.
It could be worth asking the agent to refactor the model so that it becomes like a classical plant model, and then you can do the control separately.
Yeah,
So it just takes a control input that it feeds to the
yeah.
And
Start by refactoring the model. So
well, before
that,
you ask it, it would be
Yeah.
also interesting to like ask it like if we wanted to ask it the question instead of telling it what to do. So like if I wanted to refactor this so that we could do this control, what should it look like? Yeah.
Yeah, that's a good way to do it. Yeah, propose how to refactor the model so that the
Yeah, because if you just say do the refactor and you give it a statement that's not explicit, it's going to start filling in details for you. But if you instead pose it a question, so you have the back and forth, align the mental model with what it's about to do, then you're going to have a much better time.
So we'll have it going through this, but I think at the same time, what we can do is we can find out. I think that the question that we're going to want to have, yes, we're going to want to create a few different models here, right? One with a proportional control, one with a bang bang control, and see what we can do with in terms of efficiency. Where I believe that we can measure this efficiency in terms of the coefficient of performance, right? As the suggestion was coming in from chat.
Yeah, I mean, after you get this model refactored, right, we'll probably have to tell it to implement a component for the heat pump, right, that relates the heating output with electrical energy as well, right?
Yeah, with 3 controller options, one's bang bang, one's P, one's PI. Actually, this is kind of perfect.
Yeah,
it's kind of exactly what I was describing. Just do
that.
See what happens when you don't tell the agent what to do and you ask how would you do it?
Yeah, exactly. It is really a very big difference because I mean it worked great in this time in this scenario, and sometimes it could miss some detail, and it'll be such an easy back and forth. It's really the superpower.
And we also have a new chatter coming to the Twitch chat here, which is saying maybe also adding a more complex model for the heat pump could be interesting, or giving it power through a solarish energy source and external grid, but let it minimize the total power needed from the external source while staying in an acceptable temperature range. Yeah, I mean, this version of Dyad, I don't think will actually have the full heat HVAC model system inside of here, right?
But it would be really nice to try and at least attempt the request with what we have. I think this is certainly something that we can do. We can also add Dyad Model Optimizer, and that would be really cool to
well, I think what we'll have to do here is we're going to have to take the model that we have, and we're going to have to continue this in another day where, so for those who don't know, we'll I mean, you know, we don't have to start from scratch every time. But basically though, okay, we have an HVAC model as part of Dyad. It's not in this version or not being released, you know, as part of this pre-release right now. But the thing that we have inside of there is things like two-phase flows, specific refrigerants modeled and everything. So we can do a complete, you know, very clear, exact model of this heat pump as well. And we can swap that in there and see what that changes in terms of like, okay, if I use refrigerant 1 versus refrigerant 2, what is the power and performance that I get out of this, right? So yeah, we could definitely do that as a follow-up here. I think
that model would probably be more appropriate for like designing the heat pump, but I think if you just wanted to run something that was a heat pump with some like efficiency characteristics to get an understanding of energy consumption, that actually might be a model that the agent could build even right now, right? Something that was, you know, efficiency based on the temperatures outside and the temperature inside, right? And that'll give you some kind of varying COP that would then give you varying energy.
Yeah. So I think that So I think that those are going to have to probably be 2 different live streams, right? One that's really focused on. Well, I mean, there's this one which we'll go into like, you know, the power efficiency and everything of this, right?
Yep.
And then we'll go into another one and just saying like, okay, we start with the model of a room, which we just constructed right here, right? And now we just go, okay, now let's act like we're Mitsubishi or Carrier and trying to come up with a new design of a HVAC system for, you know, and let's see what the optimal design would be, right? So we could do both of them, right? We'll just won't be able to do it all in one sitting. This is starting to look like my day job. Yes, it could be like your day job, but is it as fun as your day job?
It's much faster too. So I mean, in the span of what we've been, the key thing to highlight is we've literally written nothing, right? As much as this whole experience has been like amazing and that we've been building models and plotting, we've been writing very small amounts of text, and most of the code and writing that you do at your day job is actually being handled by the agent. And notice that in our particular case, what we're really doing is only verifying along the way. And that's really kind of the key shift in the workflow when it comes to using the agents in these kinds of situations.
Yeah, so it implemented the bang bang controller, which is using a bunch of if statements and everything, but the discontinuous switching hit some numerical stiffness. So it swapped out the solver, and that seems to have done the trick. So yeah, it figures out a lot of stuff.
Yeah, it's really good. It's really good. Like with the debugging especially, and this is really cool. We should do an animation. Can we get the geomachy animations out? I mean, that has to be the final bit here.
Yeah, we'll end it with some geomachy animations. You can't do it without the animations.
Of course.
I mean, the agent likes to go overboard on these animations too, which is kind of the best part.
Chris, can we look at how it restructured the model into a plant subsystem now, and then put the controllers next to it?
So this looks like it's the core.
No, this is a test component. This is the full model.
The test component. Okay.
The one above it, yeah. There we go.
Okay, so here's a plant model. Okay, and it has a real input and a real output. So it's doing this causally, right? Where it's just saying, okay, I have a heat pump input and a room output, right? And then it says, okay, component day night set point, which just has an output. Okay, that makes sense. And this is then being done through a switch. So it changed it from being just a sine wave to being something that's now doing if else for the day night cycle, which I think is probably a better model, right?
I think that the refactoring with the agent from something that like starts flat and goes to components, which is kind of a natural evolution often of kind of the way models go, is super cool to see the agent just like, create components, subcomponents, compatible interfaces, reconnect everything, test to see that the model is the same as the flat model. It's pretty cool to see, and it's a lot of work that kind of saves you from having to do manually.
Mm-hmm. All right, then so then we got a bang bang thermostat, which looks like let's see, the air is so it's going to be if air is so it has a deadband in there to avoid chattering. Okay, that makes a lot of sense, right? And so then so it has wow, that's actually a pretty sophisticated bang bang thermostat that I came up with. Yeah, that makes a lot of sense looking at it. But I wouldn't have at first myself. I probably wouldn't have put that deadband in there. But I could see exactly what it's for. Yeah.
And then you would have hit the max hitters and never gotten out of it.
Oh, for sure.
And it just went off and did the solver. I mean,
just chattering right around your set point.
Yep. And then a proportional controller. So this proportional controller is it's okay. So the if else is just for clamping to the physical limit. Okay, that makes a lot of sense. And the PI controller probably has a clamp as well. Integral term with the anti-windup, only integrate if not saturated. Yeah, okay, like these are it really figured out a pretty reasonable control kind of system right off the bat here.
And it implemented the PI controller, right? But it could have also used, if we had told it would have used the one from the library too.
Yeah, it could have used the one from the library, but it did actually implement it with anti-windup, which so our controls engineers would be happy about this.
Nice.
All right, and it looks like the agent is finished here. So all three controllers work. Here's the comparison. Set point track. Let's actually just look at the.
Can you animation? Just be like.
Well, here, generate the plots and tell me the not URLs, file names.
File names.
Yeah.
Also, Chris, it would be while it's doing this, it'd be worth just to scroll through when it ran the controllers, how it validated them, like the different scenarios, so people could see that this is, for anyone that's joining new, that it's actually doing expectation versus what the set point is supposed to be, and it's handing things over and looking through the data and making sure that things are aligned with expectation.
Yeah, and all these scripts should be saving into the scripts folder as well, right? So we could go back through them if we want to look at this, but. Yeah, it's validating that everything is in reasonable ranges and such.
Yeah, and it prints out the trace and it looks at the numbers and it makes sure that temperature is sticking with the set point. Yep.
Mm-hmm. Okay, I see plots are pumping in now.
You can also use language. Look, I want pretty plots.
Oh, the bang bang controller is really going. I can see why it needed a better solver to handle that. Yeah, that's it's really turning on and off. A realistic system probably does not turn off on and off all that much. I mean, I know one of my neighbor's heat pumps, so I can hear it, and it does shoot on and off like every 5 minutes or so. But yeah,
I
you
mean,
can see the Bang
and
Bang
this is one of the
controller.
things, right? We said build the Bang Bang controller, but we didn't mention, like, how often should the controller operate in terms of frequency. So it just kind of filled it in. This looks great.
Let's see.
So you can see the proportional doesn't quite cut it, but the Bang Bang.
Yeah,
is
the proportional's not getting into the desired parameter range here,
And
right?
it did say that, though, right? Like, if you go back to the agent, it actually said the controller right here that it reaches this is too cold. This is expected for P only. And then it does the PI, and then let's see what it says.
Why would a proportional control not be able to do this? And yeah, we have someone in chat says, "Yep, this is going to kill your compressor." Ha ha ha. Yeah, they were. Yeah, so that's why you want to refine your model and controller a bit before you put it onto the real world system.
And also, like, when you ask it to build you a controller, you should speak about your specs explicitly up front as well. I think this is one of the key things about this, that it'll go figure off, and the details that it'll assume, it'll try to make it as physically realistic as possible, and unless otherwise stated. So, yeah.
Well, is it known that P controllers cannot accurately hit a set point here?
Yeah, I mean the steady state, right? Once the proportional error gets small, right? Then the input it just can't. There's not. Yeah, so you need the integral part, right? It was proportional only, not PI.
I see. Yeah, because as you get close enough to the steady state, then your actual changes start going to zero. So it actually I've seen this when trying to use PID controllers for trying to make RC cars like go to a line. Yeah, and if you only use proportional controller, then it doesn't ever go to the line. It gets stuck, right? Yeah. So I remember that teaching example back in my controls days. So. Yeah. So that's that same effect right here. So you have to have some kind of integral control, otherwise you have a drifting error, which is actually the same thing that happens in automatic differentiation, by the way. Yeah. So okay, that makes sense. But then I guess the issue here is we should probably make sure that our Bang Bang controller has a set frequency that's allowed to change in, right?
Yeah.
To be a bit more realistic. What's a realistic, like maybe like 5 minutes or so, or?
Well, instead of guessing, just mention the observation. I'm looking at the plots. The Bang Bang is going off too often. How do we fix that? And
plots. The Bang Bang is unrealistic because it's firing too often. And watch, it solves it by saying, all that you need is a second Intel computer.
Okay.
Increase the deadband, a maximum on-off time constraint, or add a rate limiter.
I mean, the deadband increase is an easy one. That's just the. So what was it before? It was 0.5 plus or minus 0.5 C.
Yeah. I guess what's the realistic one? I assume that realistic realistic systems would both have a larger deadband, but it'll also have a time limit as well. Or?
Yeah, it would probably not allow on and off within a certain time too.
So what do you think is the right direction to go here?
I don't know. Just try option one because it's simple and just to prove that it made the change, that it did the right thing.
Oh, and Chris, tell it to view the image. You can hit escape and tell it to also view the image at the end so that it can verify it's. Yeah. Anyways.
I think
it
it'll
doesn't
go.
need to. I guess I just
yeah.
want to show off that it can read images and do stuff like that.
Mm-hmm. Yeah, and we got Avinash in the YouTube chat saying day 2 with Dyad HVAC. Smiley face. Yeah. So the developer of the HVAC models actually wants to join in. He put a smiley face in there. So I think that in the next one, I think that's a very good. That's probably a very good thing to look into. Yeah, I mean, Yeah, because I'm always curious. I guess I've heard a lot from like the Mitsubishi engineers and everything about like, oh, the differences of refrigerants. Like, refrigerants, like you don't want to use like some of these efficient ones because they put CFCs and kill the ozone layer, right? So we changed them and we use things that are flammable instead, like propane and such, right? But it's too flammable, so we end up using this other kind of thing. And I'm kind of curious, like, okay, what if we just didn't care about children, right? We just used like propane instead of as our heat pump, right? I'm curious, like, what is the efficiency loss that we have, right? I don't know of anyone that's actually put that somewhere in a paper or something, right? I'm sure someone has, but we can probably calculate it out right here and just see, okay, 30% of energy usage is because we don't want our HVAC systems to explode and kill children, right? I mean, then we as a society can say, do we value children this much, right? That's a value judgment from there, but we could at least do the mathematics behind it, right? Alrighty.
I gotta get that prefix where it keeps printing out the license. The local preferences isn't getting copied over.
So yeah, it looks like it's just doing some simple changes to the deadband, and then it's compiling and testing this out. Yeah, and just to reiterate for people who weren't here at the very beginning of the stream, right now the test run cycle is a little bit slower than it's supposed to be, just because it's not on the latest version of the modeling toolkit, symbolics, and everything. We just had the entire symbolics system just changed in order to make sure that it had full pre-compilation and much faster turnaround, and with compiles and such. So. That is a update that will be going through and entering Dyad sometime in the December timeframe. We're going through the release process right now, and that should make the turnaround here be much snappier. But again, what we wanted to show here is just, I mean, the agent's already run and the agent already does cool things, so let's just start playing with it, right? So almost all the new systems in Europe are using R290 propane, by the way. Oh, I didn't know that everything's actually using propane now. I would have thought it would be too unsafe. I mean, like with the EU, I kind of like look at things like, like this cap in the water bottle, right? And I just kind of go, yeah, I would have assumed like the EU would have like, extra safety measures or something involved that beyond that. But okay, so R290 is actually directly propane. I didn't actually know that. All I knew is that like 5 or 6 years ago, one of the engineers at Mitsubishi had told me like, oh, yeah, you can use propane as a refrigerant. It's a perfectly fine thing to do, and I didn't realize that the properties of a refrigerant actually kind of need to match the properties of things that are flammable, and so that was a interesting thing to learn. But okay, so the wider deadband helps someone a lot. It's still cycling 134 times. That's 2.7 minutes per cycle, which is too fast. The problem is that the middle state, it creates a stable equilibrium. Real thermostats are pure binary. There is no middle state. Let's make this, okay, so then it changed to being truly binary. So it realized that, okay, in order to make this much more realistic, it needs to have a much larger deadband. Which actually, plus or minus 2.5 Celsius is actually not unreasonable for the deadband. Yeah. So okay, I think that we're going to get a model that is reasonable with different versions of controls here in a second. I do want to kind of then pull out this comment here that was you could minimize the electricity power P, which is a function of Q over COP. I guess yeah. What's the right query to get? So once we have our controllers, we should probably start to ask it, what keeps comfort but also minimizes electrical power.
You could also just do something interesting. Would be like, how would we address this comment, and just copy pasta literally, and then it would.
Okay.
Yeah.
Yeah. Okay. That sounds like the funner way to do it, I guess. Yeah. Just directly
Because
take the comment and let the agent figure it.
I
Yeah.
mean, it's because as long as you're posing it as a question, right, it's gonna go do its search and understanding. So even if it made a wrong assumption, it's not gonna implement code. You're gonna see what its thinking is, and then we can have that back and forth, and then voila. Also, there would have been so many cool things to do earlier on as well, where it made the decision of like, there's no in Dyad, there's no state memory, so we could have done this, but we could have asked it, well, how could you do it in Dyad with what it has, and that would have also been a fascinating way where it figures out exactly how to still give you the thing that you want without it saying that there's a limitation here, and let me just give you something simpler. And that's typically LLMs will do that in general. This is kind of like just upstream behavior. They want to deliver a result. But here, obviously, in navigation-wise, you hit escape, you tell it what you want. No, don't do this. Don't simplify it. I need you to do this instead. And it'll go ahead and do it.
Yeah, I think in this iteration of the agent, to be fair, we also don't have the model optimizer docs. So
that's fair too. That's fair too.
It wouldn't really know that this capability exists. But maybe that's something for next time, right? We already need to start the content plan. So
This stream is brought to you by Agos das Pedras.
Gotta put sponsor in the subtitles.
I wish Petrus would sponsor us. I just get free drinks all day. I just only drink Petrus.
All right, it's in the assets.
Oh, did it already regenerate it? Oh, I see it going. Yeah, let's give it a second here.
I'm surprised you guys enjoy the flat kind of just static plot. I almost never ever have it giving me a static plot. I'm always like getting into like anime stuff.
I'm very unaesthetic, right? I'm in a blank room right now. I don't know. I don't need my Instagram, my interior design or whatnot. I'll make it make an animation, but like it's just overkill for me. But yeah, we'll end it with a bit of pizzazz. It's fine. Where is your Intel processor? Oh, the Intel processor's in the room. Don't worry.
Yeah, and it's actually doing more than res body rate of a human being.
Computer right here. Yeah. Oh, you're talking about the interior design. Yes. I mean, the interior design does have a computer. This is a desk and drum kit only room. But the drum kit's beautiful, right? So, you don't need anything else. All right. We got our, let's do the control comparison combined. Here we go. In the first 6 hours, and all right, let me. Yeah, so you can see that the Bang Bang controller is having quite a difficulty to try to actually get around the desired range here with even with that much larger deadband. How often is it doing the switching though? It did say this in here, right? That is switching every like 2.5 minutes or so. I guess that's reasonable. Yeah, this okay because this is 48 hours. So yeah, you can see in the.
It looks weirder because of the fact that it's 48 hours, but you have to kind of zoom in.
Yeah, it's really turning on. Like yeah, this is I guess yeah. This is proof that if you want to be keeping to a good temp, you either need to, if you're in Boston and you want to be at a comfortable temperature, you either need a variable rate heat pump, or this heat pump is going to die in 5 years. It's just the heat the amount that is heating and then releasing the heat is just way too fast to keep it in a realistic range. Yeah, that's wild.
I think it gives.
I was looking at. Well, temperature control comparison over 48 hours. Yeah, so it's looking at the full 48-hour span.
But did it just generate one plot, or did it generate more than one plot? I think it generated more than one, right?
No, these are the 4 plots altogether. This is a combined plot.
Weird. I saw it list more than one file in the response.
Yeah, but it's these 4 and then the combined one.
Oh, interesting. Understood.
Yeah.
And I mean, ultimately, that deadband temperature, I mean, that's like probably uncomfortable in terms of how that's like a 5-degree Fahrenheit swing. So I mean,
Yeah.
that's probably more than people would be willing to accept around their set point anyway. So,
And it's still pumping on and off a lot of the time.
yeah.
So,
But I don't know if we actually have the. We never really looked at the heat loss side, and maybe we just we don't have that part correct. So there's lots of things. Even though the agent comes up with stuff, right? We gotta review all the parameters and look at it, right?
But yeah, so I guess let's give it this.
Yeah.
Let's give it this comment.
Yeah,
We
why
got-
you do that, Chris? Yep. Sorry.
Hey, Mr. Agent, you're on candid camera and being shown in a live stream right now. We got a comment from the audience. Oh, sorry, I'm trying to figure out where this. God dang it! Where did the quotes actually go on this Portuguese keyboard? There it is. How would you address this by making some plots
Well,
of
yeah.
the different controller results?
If you ask it to make plots and you ask it in the same sentence how to address it, then it's going to like give you what it thinks and immediately go versus pause. So
I think that's fine. I think that's fine.
okay. So one shot it. All right.
Yeah, let's one shot it. I can see why having the name for an agent is pretty good. I like calling
Yeah.
things Claude and stuff. Yeah, we
That's what I'm saying.
Maxwell is a good name. Maxwell is a good name. Maxwell sounds like more like a dog, though. I don't think I've seen a human called Maxwell for many years.
I've seen it as a last name a lot, actually. Not as a first name, though.
I am friends with A. Maxwell, first name, but he's the only Maxwell I know.
Fascinating. So what did it say before it ran off some code? It just kind of went at it. Did it say, I just want to scroll up what it actually said for the plan.
Excellent question from the audience. They're asking about electrical power consumption, not just heat output. Heat pumps have coefficient performance that varies with conditions. Let me create plots comparing the electrical energy consumption of each controller. Yeah, so let's see actually whether the variable rate one is truly better in terms of energy consumption instead of just using the bang here. I'm curious. I mean, are variable rate, like, I guess the question is, if you only allow an on state and an off state, can you actually make your HVAC system be more efficient? I would assume so. I would assume so, right? But then you would lose some because it needs to be doing all this control stuff, right? But I would assume that what you'd need to make sure that you model your HVAC system as more efficient if you don't allow for the variable rate. It's just more efficient at its one rate that it's running, and the inefficiencies due to turning on and off. I wonder if it will have an effect like that. But I also don't know if that effect exists. Maybe it's worth just kind of digging around on the internet a little bit. All right, let's look at this. Control efficiency analysis is what it came up with. Yeah, so the bang is actually more efficient.
But did it maintain control or no?
Well, it says that the average temperature from the bang is oh, I guess. Well, it's telling us the average temperature against the comfort threshold, but it's not missing the variance in the temperature, right? Or it's missing the variance of the temperature, right? Bang is most efficient, but also we should look at the variance in the temperature to know if it's actually comfortable. Interesting. Okay. I mean, I was just kind of espousing live just to say I would think that Bang Bang is more efficient, but I wouldn't have thought it was that much more efficient. That seems kind of wild.
Well, I guess in the perspective of the assumptions that we have for the model, then yeah. But perhaps if things were a little more realistic, the outcome might not have the same margins.
I'm curious if we could look into that in a second, find out why it's so much more efficient. Oh yeah, okay. Because it has a high COP while it's at the maximum. Yeah, and that's like what I was thinking in my head, right? So I guess, yeah, the person in chat here, on-off control is considered bad for efficiency because it will increase the supply T beyond what is required to match the room heat loss. Yeah, but I guess I mean, if it's running at full capacity, that's going to have a higher coefficient of performance, right? And because of that, I guess it actually ends up being more efficient. I guess that's my question. Is this something that we see in reality, or is this something that isn't matching a realistic result? But I guess the other thing to note here, though, is probably that it's probably not going to be a very very comfortable control system, though. So.
Yeah, I mean, you need to look at the details of the COP implementation. Oh, cool. Time in different temperature zones. Nice.
Yeah, the variance in the temperature is
those are pretty cool plots.
So yeah, even though the Bang Bang controller has a pretty good average, it's only in the comfort zone for a small amount of time. Only like 50% of the time are you actually comfortable. So you'd be taking your jacket off and putting your jacket back on every 10 minutes, but you would save a lot of energy. I mean, I feel like if it's just me, I mean, if this is the model of a bachelor pad kind of thing, right, where there's no furniture or anything, there's just a bed on the floor, right? This is the optimal way to live, right? You know, like I think that we should go to all the other Twitch streams, and whatever dude is running that Twitch stream, you know, we should be like, hey, stop your Lethal engines right now for 1 second. Go to your HVAC system, turn it on to Bang Bang. Just have it so that way your jacket's right there. Take your jacket on and off, you know. And as you start to rage, you know, maybe you take your jacket off as you cool down because you get a double kill. Put your jacket back on, and you will save, you know, a whole lot of electricity, right? Like what's the amount of electricity that you save here? You save, yeah, like.
But Chris, this was with the PI control that never reached the desired target, right?
Oh no, the proportional doesn't reach the desired, but
but it
PI
switched.
controller.
We switched it. Okay.
Well, the PI controller hits the desired. The proportional does not.
Okay. All right.
Yeah. So I'm kind of ignoring the proportional.
We don't actually encode the startup cost though here, right?
Yeah, the PI is pretty much tracking it almost perfectly. We don't have the startup costs here. That is true. Is there a startup cost to the
Oh, there system? It is. 3.5 less than the PI, but a higher variance of 3.4 degrees Celsius. Interesting.
Yeah, so let me go find that plot again. Oh, there's a cumulative energy consumption. Yeah, so it's assuming that the startup cost of starting up the HVAC system is 0. I don't know if that's a good assumption. Maybe we can ask that in a second here.
Yeah, it's definitely not a good assumption, and it's also not good for your system overall, right? So there should be some long-term penalty from starting it up and turning it off so many times an hour, right?
Well, in the chat here, there's a very good idea, which is you could cycle the Intel CPU on and off to dampen the oscillations, right? And you can do this with your GPU as well, right? So you have it at like, when your HVAC system's off, right? You could have this like compensating behavior where you turn it on to 4K when your HVAC system's off, and then you have it so that when your HVAC system turns back on, right? Like you can make it so that way it has a dampening effect, right? And maybe you could get even better thermal efficiency. Yeah, we gotta go to all these Twitch streams and be like, here's an Arduino device that will set your screen settings to based off of your HVAC system.
Wait, actually, Chris, can we actually ask it to use the Intel computer processor as a load balancer? It'll be so hilarious. Please, let's just see what happens.
What was the other thing that we had? Should there be a startup cost each time the HVAC starts back up, right?
The one comment I do want to make is that, as much as we're having fun with this and kind of building a model along the way, we've used the agent internally for some very serious things, from translation to building models from scratch as well. And so it's not just the simple models that we're dealing with right now that kind of fit within a stream time that the agent is capable of doing. As we've kind of, displayed throughout the journey of building this model, that whenever it gets to kind of these tough situations of what to do next, it always knows what to do on that level. And when we scale to larger problems, we find that this behavior that we see for these simpler problems maintains a consistent behavior for more difficult things. As long as you follow those kind of practices of like post things as questions, get the right plan, align yourself, then let it go off. And just wanted to kind of make that comment as well.
Let's see. So it's saying that yes, okay, the good observation that there should be a startup transient cost. So either a simple energy penalty or a realistic transient COP. I think maybe just go with option A for now, just to kind of eyeball it. I guess, John, do you have a preference here?
Yeah, start simple. I mean, just to see that it did the right thing, right? You can always tell it later to refine the approach, right?
Oops, completely misspelled that, but it's okay. It's
But this would be a really fun model to refine, because I think with a slightly more detailed implementation of the heat pump, right, something that is dynamic COP with some some interior states for how much it's cycling on and off, you could probably get a pretty good answer from a model that doesn't require all the super cool HVAC stuff, which we'll show later. But I mean, I think those are the more appropriate models for running long periods of time anyway, right? So.
Yeah, and actually we got a comment inside of the YouTube channel, which is kind of interesting. So more than running at full, running at the nominal rate maximizes the COP. So I guess we can maybe try to make it so that way the PI controller tries to keep things at the nominal rate instead. Maybe there's a more efficient thing than just trying to do a pure PI, right? That's trying to instead go to the nominal rate more often. Or
no, I think that's a comment on the heat pump model, right? That the COP kind of the COP is maximum at the nominal rate, which may not be the full power rate, right? So it's a requirement really on how to build a more detailed COP model for the heat pump, right, and how it's specified.
Yeah. So okay. So with the startup cost, it's still saying Big is more efficient. So 2.6 per times more energy for perfect comfort, or save money with the temperature swings. Unless we have another idea in here that we're missing in the model, it sounds like we just got to get back to wearing jackets.
That always helps. Where was the total energy? I didn't think the total energy difference, was it really that large? The 2.5 times?
Yeah.
There was a plot of the cumulative energy, and I didn't think it was it really? Maybe I didn't see the scale.
Yeah, this is the cumulative energy, but this is without the
Okay,
the
yeah, it
costs.
is. Okay, 30 something. Okay.
But then when we add in the startup costs, you can see that there's a decent chunk in the startup costs. But yeah,
it did something. Yeah.
So highlight what you're learning about is so we have so let's recap this a little bit. Now we're kind of getting close to the end here. So we created a full thermal model of a building, but we then refactored it a bit. So let me show the refactored version here. So here's our plant model. Our plant model has an input from a heat pump, and then it has an output to the room. And then we have air in this room, which acts as a heat capacitor. We have an ambient signal, right? This is just the ambient temperature of Boston during the December. So just matching some averages. We have a thermal conductance through the wall. We have a solar radiation cycle going on. We have an electric space heater. We have a heat pump, which is then going to be described with a control system. And then we have our model of our room. So we have a computer, specifically an Intel computer, so that way it's 150 watts, right? Then we have 2 humans in here, and we also have a drummer because we support the arts, right? And then we have a temperature sensor. So this is our what's the word? Our plant model. And then we have the day-night set point, which is being done through just a switching model between the temperature in the day and temperature at night. Then we have our control system. So we have a bang bang thermostat, which has a deadband implementation for some hysteresis. We have a proportional controller, which there's issues with proportional control, which we discovered, or I guess rediscovered as part of this. And then we have a PI controller that is then controlling that HVAC system. And so then we have the built-up models with the bang bang, we have the proportional, we have the PI version altogether. And so now what we did was, what are we learning here? Well, what we're learning is that when we put this all together, we saw that the version of, if you have a PI controller, you can really, and you're using the variable rate of modern HVAC systems, you can really match this comfort level, right? Where you say, oh, this is more comfortable during the day, this is more comfortable at night. You can really match your comfort level quite well, right? You can see like the green line is just right on top of it. Whereas your bang bang controller is, it's turning on your HVAC system, turning off your HVAC system, always putting it to 100 efficiency, 0%, right? It's very difficult for that to really reach the right temperature. But when we look at the power consumption, right? Let's see. Where was this again? Yeah, when we look at the power consumption, we're seeing that the bang bang controller is actually much more energy efficient in terms of its total energy consumption. Though, where was the comfort analysis? Yeah, but in the comfort analysis, we can see here pretty clearly that the variation in the temperature is much higher for the bang bang controller. You're really getting outside of the comfort zone for about 50% of the time. But if you allow yourself to do that, then you're a bit more energy efficient, right? And we can actually then see that with startup. So the last thing that we added here was we said, okay, every time you turn on the HVAC system, there's actually a cost to an energy cost to that. So let's make sure we add this into the model as well. But even when we count in the startup, the bang bang is still 2.5 times more energy efficient, right? So yeah, I guess the main thing here is like, is there anything that is clear that we missed in this model, or is that the result that we just got to tell people, bang bang it, and if you want to save energy?
I think the result is that we have a very simple COP model, right? So
yeah, probably. So we might need to come back and so Avinash is in the chat and said maybe we need to do this with the full HVAC model. Yeah, we might need to come back and do this with the realistic HVAC model, with the modeling everything about the compressor, the heat pump, and the refrigerant and everything, and see if that actually changes the results. Yeah, because the coefficient performance might just be too simple of a model here.
Yeah, or even a simpler model that has a more realistic COP, right?
Mm-hmm. Mm-hmm.
Could still move you in
I mean,
direction.
can we ask it that? Can we get?
Okay. Ask it. Is the COP model realistic? Is this the question here?
Yep.
Let's go for this, and then if after this, I think that we can tell it to create some finalizing animations to summarize all that. I mean, I walked through the summary, but I'm curious if the model can summarize it as succinctly as I got it there. Yeah, I'm curious if Let me look on my other computer. Is bang bang HVAC more energy efficient than variable rate? Yes is no. Yeah, so let's see if that ends up being because of the COP model.
And actually, if we had gone
Simplified
back to,
but reasonable.
if you went back to the bang bang control, that was more a smaller, dead band around the desired, then it would have cycled more, right? And then you would have had more of these penalties. But then your comfort would have been a little bit more equivalent, right?
Well, okay, I guess that's the thing. Yeah, that is. It's not even comparable in terms of comfort, right? So
yeah, it's hard to compare when you're not roughly at the same comfort level, right? So, I mean, no energy usage and uncomfortable will always win, right? So, I mean,
yeah. All right, we're going back to just caves and fires. That's.
But I mean, it is interesting to ask the agent, like, hey, is this a good model, or how would you make this model? Can you propose some options for making this model more?
It's interesting that it mentioned that the biggest issue was that the coefficient of performance model that it has right now biases towards the bang bang more than the proportional controller. Kernel model makes proportional/PI look artificially better.
It looks better because it allows it to be very uncomfortable.
The bang bang seems to look better because it allows it to be very uncomfortable.
Mm-hmm.
So was there? We ran this whole thing. I didn't really look in detail at the model, right? What was it using for the COP? Was there a penalty when it wasn't running at max power? I mean, of course that'll hurt.
Let's look at the. I don't know where the COP model was.
Oh no, you've reached the end.
Oh no.
So for folks who see this, I mean, in the release, we'll have the automatic compacting feature, which means that it'll summarize the conversation of what's happened so far, and then it'll allow you to kind of continue. But in this current version that we're demoing, that feature is not in here yet. So.
Yeah, well, that might just be a good place to end then, because I was just about to do the wrap up. I know that you wanted to create some animations or. But with the current version of the agent, right, we'll have to restart the context or whatnot. So it might just be a good, that just might be our exit. So
yeah, I mean, the coolest thing about this whole journey is that we literally sat down and wrote no code. We took suggestions from people, all over the world, and we didn't even use the right grammars really, and ended up building a relatively decent model with physics that got verified and validated before handed over. We got plots going back and forth, refining as well. We got the refactor too. I mean, this was an incredibly productive hour-and-a-half session that could have easily been probably north of 3 if you had to actually write everything on your own.
Yeah, so let's take some notes. So I think that one thing that we want to do in the next one is, let's take a model of a room and let's really do this with a realistic HVAC model. I think that'd be a great case to do. And I think another thing to do would be to look into taking a model of a room and generating thermal flow images and a 3D kind of rendering of it, right? That might be a pretty cool thing to do.
Yeah.
Other takeaways from this as well?
Yeah, another thing I thought we could do, I don't know if we have the capability for it, but we could try and hook this controller up to a Trixie.jl, like actual simulation of a real room with a real CFD. I don't know if we can integrate that into Modeling Toolkit, but that would be pretty sick.
I don't think that we'll be able to integrate that into Modeling Toolkit. Yeah, the co-simulation there might be a bit rough.
I think you could probably get away with an integrator and the Modeling Toolkit inputs thing, but we can figure that out probably later.
The cool thing is
that before we go live with that, yeah.
Well, you could,
but
you could just,
you
could just not even have it use Modeling Toolkit, right? You could just have it do the, if you just wanted to show the Trixie thing. I mean, it would be able to do that as well. But I think what's really cool is the Dyad modeling toolkit ecosystem itself that has all the stuff that's going on. I mean, we could also discretize the room, right? We could actually do that. You could literally discretize the room and then make your dynamics more than just be a lumped model. That's also something that we could do.
Yeah, we can discretize the room, and so we don't need to make it as refined as having a complete mesh. I mean, having a room be a rectangle or whatnot, and we just say the drummer's at one spot, and we put the drummers in one spot, the computer's in one spot, human sits here, and everyone doesn't move or whatnot, right? I think that we can do that and kind of start to see if we can get a spatial version of this model that's rather simple, and see if we can and see if we can look at if there's any dead spots, right? Any spots that are, okay, if the heat's all coming in from right here, right? Is it going to be warm enough on the other side, right? Or will that change how we do the control system? Does where we put the thermostat actually start to affect it as well? And does that affect the efficiency of the heating, right?
One other thing as well, Chris, is that doing more downstream stuff. So we did a lot of model building, but then using the models to do stuff with it would be cool as well. So I think one person in the chat earlier suggested the idea of the more complex heat pump model and giving it power through kind of I think it's solarish energy source and an external grid, and then let it minimize the total power needed from the external source while staying at an acceptable point. Like those kinds of downstream situations, I think that would be really cool to show as well, because we've done things like that. And much harder so, and that would be really cool.
And there's also a suggestion of using SVG to mesh. So maybe I could just, maybe what I could do is I could actually just take a picture of the room, right? So I can use this actual room here. I could take a picture of it, and I can tell it, hey, create a model of this room, right, where the drummer's right here and everything, and they can do the discretization. So we could let the agent go directly from the image to model, and okay. We got a lot of ideas. We're definitely going to be going live next week again. I would say that this live stream was a hit. We're doing this again. We're doing this again. We have something to figure out in order to make sure that we can have the chat overlays and everything. But thank you everyone for joining. I think that this has been fun, and I think we're just going to start doing this as a regular little bit here, just creating models with the agents and continuing to show new features of Dyad. I think that this is much cooler than doing a feature, like a feature release kind of README. Let's just get the agents to start using it, build models, and we'll be taking your suggestions. So I think next time we might continue this model a bit, just to play around a little bit more. We'll start right here, and then we'll just continue and continue improving the model. But definitely one of the things that we want to do is we want to take ideas for what to model from the audience. So if you have things that you want to share, just send me an email, or we can come into chat next time and just say, build a model of this car or whatnot, right? Because what we've been really doing is we've just been doing all this live and just showing people the agent tends to generate things that are pretty good, and the only way to really show people that is to do it, right? So we'll be back. I'm having a lot of fun, but for now, I think that we'll cut right out. And thank you everyone that joined, and thank you everyone that joined in chat. And I hope to see you next week.
Yeah, thanks, folks.
Thanks, guys.
Thanks.